Hold on, I kind of losing control of it. Right. All right, it's recording current. No problem. Of course, your discussions will be privy. If there's any background noise, just bring the background noise to a minimum. Okay, so we're looking at this question. Discuss the importance of alternative energy to the Caribbean reference to two sources and their use. So let's ask the question. What are some alternative sources in the Caribbean? Let's ask Alexia. Can you contribute to that? What do you think? Give us an exact example. No? Hello, Alexia?
Hello, sir?
You can tell us anything about any alternative source of energy in the Caribbean? Any idea?
Well, wind energy.
Okay, so good. Anybody can tell us where we have the utilization of wind energy in the Caribbean?
Jamaica.
Yeah, well done. Agreed. Another source of energy, Daniela.
Hydroelectric.
Where do you think we have hydroelectric in the Caribbean?
Guyana.
Yes. How you spell Guyana?
G-U-Y-A-N-A.
Is it? I have it correctly?
No. G-U-Y-A-N-A.
Oh, right. So, yeah, okay, sorry. I can't spell too well. Okay, yeah, that looks correct. All right. What other source of energy that we have in the Caribbean? Alternatives. We have two here to cover. But we're going to cover some more. How about that?
Yeah.
And where?
Sir.
Yeah.
Sophia said how her mic not working, she could only hear.
That's great. That's not a problem. Once you get here, that's important. All right, so we have three examples, right? Wind in Jamaica, hydroelectric in Guyana, solar in Barbados. There's one more I want to introduce, which is what is that?
That's with
The heat from the earth or something.
Wonderful.
Yeah.
Well done.
Italy. I think it's like houses and stuff.
What country?
Still St. Lucia.
That's correct. Well done. All right, so these are alternative sources of energy in the Caribbean, right? Good so far? And discuss the importance. Why is it that this is important, alternative source of energy in the Caribbean? It's obvious that the fossil fuels, some of these countries do not have fossil fuel historically, and they have to import fossil fuel, and fossil fuel, of course, is a non-renewable source. Every one of these sources that I listed, they are renewable sources of energy. All right? So the first point is that most of these countries these sources are listed as renewable sources, and it provides them a sustainable supply of energy.
Hello?
Right? So, I mean, you know, they've discovered a lot of hydrocarbons in Guyana, but historically, I'm talking about they've not accessed any reserves of fossil fuel. Barbados trying to steal some natural gas from Tobago, but not been able to develop to that extent. Good. Next part of the question. A ball is kicked from rest, looping over the head of a hoop, 40 meter away. Describe the energy changes taking place in the ball when this hits, so when it hits the ground behind the hoop. All right? What the energy changes took place when the ball is kicked. When the ball is, what kind of, after the ball is kicked, the ball has what kind of energy? Kinetic energy. Right? Immediately after the ball is kicked, it has kinetic energy. And what happens to that kinetic energy as the ball climbs? Some of that kinetic energy yeah, you're seeing what I'm typing, right?
Yeah.
Okay. It's converted to potential energy at the maximum height. Okay. So that is the sequence of energy changes taking place as the ball climbs to the maximum height. It's up here. It's a combination of kinetic and potential, right? So here's kinetic entirely. As it climbs, the potential energy increases, the kinetic energy decreases. Up here, the kinetic energy is at its lowest value, but the potential is at its maximum. But as it passes the goalkeeper, the potential energy is converted back into kinetic energy, and the ball hits the ground with entirely kinetic energy. Right? Okay, so continue the question. After 1 second, the ball has a m kilogram v, blah, blah, blah. Derive an expression for the difference between the potential and kinetic energy of the ball. That's pretty simple. We can basically want you to have let's just see if I can write this. So we're going the difference. They wanted the difference between the potential and kinetic energy of the ball. The potential energy will be each, and the kinetic energy is the difference. The kinetic energy will be a half m e squared. Okay. Derive an expression in terms of m, h, and v for the difference between the potential and kinetic energy of the ball. That's all I could write. I can't see what else. Anybody have any other ideas on this? Do you agree? I will move forward with that. During the game, the ball has a mass of 0.43 kilograms. So what momentum is transferred to the player? Momentum we know is equal to MP, right? So during the game, the ball of mass 0.43 kilograms hits the head of a player of height 1.5 meters. The player who's standing vertically, the ball velocity at the point of contact with the player is 7 meters. And what is the momentum transfer to the player? Well, that question is a half-baked question at best. Because in order for there to be a transfer of momentum, you have to have a difference in velocity. Do you agree with this? In order for you to have a transfer of momentum, when a ball, if you've all looked at football, everybody probably saw Chelsea win the Premier League this weekend, yes? Nobody support Chelsea here.
No.
I don't support either. My daughter tells me that, so that's why. When a footballer heads a ball, what happens to the ball before and after?
It changes direction.
It changes direction and it changes velocity. You agree?
Yeah.
All right. And it all depends on where he's heading the ball. If he's heading the ball back from where the ball came, the ball will be traveling in the opposite direction with a smaller or larger velocity. You understand? So this question is half big because the question gives you one velocity. We don't know the velocity of rebound of the ball, do we? So what are we left to assume here? The only thing we are left to assume is the turning pages there. That page turning is real long. What do you all think we should assume about the other velocity? What do you think we can assume about the other velocity?
Is equal.
The 7? If it's 7, it'll come back at 7. I guess some opinions. People. You can type if you don't want to talk. Hello?
Where?
I'm asking, the ball is coming to the footballer at 7 meters per second. What is the second velocity to get the momentum transfer? Nadia, what do you think? See? What? You can type a number. Type a number in the chat window. Like, here's the chat. Instead of speaking, you could, if you want to speak, you could mute your speaker, and you can type the answers. You know, very easy. Yeah. The question is, what other velocity? Anybody? I see Sophia trying to work out the question without the other velocity, but what other velocity are you going to use to get the momentum transfer? Hello?
So we're supposed to use the acceleration due to gravity for something?
Well, not in this case, right? Because we probably have to use it later, but clearly not in this case.
Okay.
Because in this context, it's like during the game, the ball of mass hits the head of a player. Right. This is here. The velocity of the ball when it makes contact with the player. In other words, the velocity of the ball when the ball reaches the player's head is 7 meters per second. Yeah?
Yeah.
My point is that is one velocity. In order for there to be a momentum transfer, there must be a what? A change in velocity. So if we have one velocity, I'm discussing what the second velocity is going to be. Now I am willing to say it's going to be 0. But I'm trying to illustrate to you that the question is effective in that you don't know what the other velocity is for sure. You with me on this?
Yeah.
Yeah.
Because if the ball is traveling towards a player, listen to the logic. If this player is here, right? And the ball is traveling to him at 7 meters per second. And as somebody said, the ball is rebounding at 7. Do you know what the change in velocity is? If the ball is traveling and hitting him at 7, and when he hit the ball is off his head, that's the opposite direction. Can anybody tell me what the change in velocity is? The title, let's see it.
0.
Yeah, I think.
It'll be 14. How come? I'm going to just illustrate it, right? I have to use. Yeah, on it. Arrows. Oh, yeah. Good. If we have the ball traveling in this direction, right? At 7 meters per second. Everybody with me so far?
Yeah.
Right. Now listen to the logic. And then the ball hits the player and rebounds. After hitting the player, it rebounds in the opposite direction. and it rebounds with a speed of 7. Would you call this 7? Would you call this 7? Would you call a velocity of 7, sorry? What will this velocity be?
Oh yeah.
Yeah, be -7.
Yeah, you understand that, right?
Yeah.
So this is one velocity going to the right. If the ball rebounded in the opposite direction with a speed of 7, that velocity will be -7. Is this enough?
Yeah.
So my question is, which I asked earlier, what is the change in velocity? The change in velocity, as I said, would be
14. Yeah.
You see that?
Yeah.
Yeah.
And that's the point I was making. The change in velocity will be 14. Why is the change in velocity is 14? What is change? Change is the
Difference.
final minus initial, not so?
Yeah.
In this case, the final is -7, right? Not so? And what
Yeah.
minus the initial was 7. So what is the change?
-14.
You get it?
Yeah.
So the point is, they did not give us a second velocity. And the only way I could work this question, I have to make a guess. And that's what you will have to do in the exam as well. All right? I suggest the guess is that the ball hits the player and the ball goes to 0. All right? Not -7, but 0. And therefore, the change in momentum would be 0.43 multiplied by 7. We clear? But that's making a guess, not because the question is definitive. And this happens quite often with CAPE, with CXC and the examining body. So it's happening with the common entrance exam, with a few questions this year. Everybody heard about that. But what people did not hear is in the CAPE Unit 1 chemistry paper, there was a whole question that was defective. In the CAPE physics paper, there was a question that was defective, and another one that was outside the range of the syllabus. So this happens to these people every year. So you cannot imagine it's not going to happen when you're writing the exam. Okay? So you have to kind of make a judgment with these kinds of questions. Anyway, you understand that question? We illustrate the weakness of this examining body. Let's move along. Next question. This is another effective question. Have we done this question previously?
No.
No.
Good. So let's go through it. State of law. Okay. State of law conservation of energy. We get that. Let's get into the business then. What is the difference between potential and kinetic energy? Potential energy is energy due to position. Kinetic energy is energy due to state.
Motion.
All right. There's the fact that heat is lost. Does not violate the conservation of energy. When you do work, like if you're sliding a box on the floor or up a ramp or whatever, you're doing work and there's some heat being produced. Does that violate the principle of conservation of energy? The answer is, of course, no. The principle of conservation of energy is one principle that has never been violated, and we don't anticipate it to ever be violated. So, the heat energy that is produced is because some of the work you do goes into increasing the kinetic energy of the box, but it also goes into some of the energy. All right, next question.
So you could just repeat that, please.
Sure. You know the diagram I drew today in class?
Yeah.
Yeah.
Where I have, let's say I have, whatever system. We have energy coming into the system. All right, this is the input energy. And you have, as a result of what's happening in the system, you have some energy coming out. What's that on there? You have some energy coming out, right? And you have a third set of energy, which is some energy that is being lost. Remember that diagram now?
Yeah.
The principle of conservation of energy tells us, all that it tells us is this much energy here. Hold on a second, my bill. Right. Good. This energy here, this total energy, is equal to this energy plus that energy. That is what the principle of conservation of energy says, that the total energy input is the total energy output. Now, in the example I was using, you're pushing a box. You're putting in energy to push a box. Some of that energy turns up as kinetic energy of the box, but some of the energy turns up as what? Heat energy. Clear? So the fact that some heat energy is produced as a result of any operation, that does not violate the principle of conservation of energy, because the energy input is still equal to the total energy output. Everybody clear on that?
Yeah.
All right. Somebody asked the question, I don't know who it was. Are you clear on it?
Yeah, sir, thanks.
Okay. Who's that?
Michelle.
Okay.
Actually, sir.
Yeah.
I have a question about the previous question.
Question about the previous question, all right?
Yeah. Okay. So for the last one that you did, the one with the momentum,
Yes.
you said the change in momentum would be the final minus the initial, right?
Right.
So with the assumption that the final is 0, it'll be 0 minus 7, which is the initial velocity. So wouldn't that be minus 7?
Well, the minus sign is just direction.
Okay.
All right. So it's not really constant. Right? So
Okay.
momentum transfer. Yeah. I mean, there's another argument that I can present that the force exerted on the player is the direction of the initial velocity. All right. That minus 7, that minus 7 by 0.43 is really the momentum change of the ball.
Mm-hmm.
And because that ball is exerting a force in the opposite direction of the player, the momentum change of the player would be a positive quantity.
Take a repeat that, please.
What is this? The two velocities we're using was the velocity of the ball, not so.
Yeah.
So the velocity of the ball is going from final minus initial, so the change in velocity of the ball is minus 7, yes?
Yes.
Right. What is the direction of that? Minus 7 simply means that the force, the velocity change is there.
Mm-hmm.
The force acting on the ball is in this direction.
Yeah.
And the change in momentum there would be in that direction. So the change in momentum of the ball is negative 7. Negative 7 multiplied by 0.43. Somebody worked that out for me. I think Sophia worked out before here, 3.01, right? Is negative 3.01. Tell me if you're okay with this so far.
Yeah.
Yeah.
What is this? This is the change in momentum of what? Of the
Ball.
Now, what is the question asking?
Oh, it's the momentum transfer to the player.
You getting my point yet?
Yeah, I get it.
Because the momentum transfer to the player must necessarily be in the opposite direction to the momentum transfer to the ball, right?
Mm-hmm.
So if the momentum change of the ball is negative 3.01, the momentum change or transfer to the player will be positive 3.01.
Okay.
So for two reasons, the answer is 2.01.
Okay. Thank you, sir.
All right. Good. So we can continue this one,
Mm.
All right. The fun part of this is I could ask you to do questions while I go and make a cup of tea. So what's going on? Can you try this?
Okay.
This is the part B I'm talking about. I'll give you 5 minutes, right?
Sure, sir.
Let's see how far I get in 5 minutes. I'm going to make me a cup of tea.
Okay, sir, sure. Okay.
Apa? Namanya?
right, that's 5 minutes. So that I guess we all got out the first part. W is equal to mgh, which is 77 by 10 by 2100.
Yeah.
Part 2. One particular descent goes from that to that. Assuming the work done against friction is negative, potential energy change. All right. So how much work is how much is the change in potential energy? The change in potential energy is in this case 77 m multiplied by 10 multiplied by the change in height, which is 500. Yeah.
Yeah.
500. But that's a change in potential energy. They said in the question that assuming that work done against friction is 90%, right? In other words, of this energy, 90% of this is being converted via friction to heat. So really, only 10% of this energy, is converted to an increase in velocity, meaning increase in the kinetic energy. So we have to multiply it by 0.1. That's 10%. Okay? So this here would be equal to the a half mv squared. All right? Good? And from there, all right, it's 10% because they said that 90%, assuming that the work done against friction is 90%. So if 90% of this potential energy is being used as friction, that is going to be converted to heat. 90% is being converted to heat. So therefore, if you convert 90% to heat, you only have how much percent remaining? 10% remaining, right? So if you have 10% remaining, where does that 10% go? That 10% has to be converted to kinetic energy. See it? Yeah. Got it? 0.1 is 10%, Sophia. 0.1, this 0.1 here is the 10%, right? 10 over 100. No problem. We good so far, everybody? But this will be increase in speed in meter per second, so because all of these are in SI units, so you don't have to convert this velocity obviously to kilometers per hour. We all know how to convert from meter per second to kilometers per hour.
Yeah.
All right, so we'll leave it at that. We're good with that question so far. Everybody understand that? What is the average rate of energy conversion of the cyclist and cycle if the descent takes place in 1 minute? Again, this is an ambiguous question. What do you interpret this question to mean? In my estimation, it's an ambiguous question. What do you all take this to mean? Read this again. What do you take this to mean? They said the rate of conversion of rate of energy conversion. What do you all think? I can argue two different answers here. It could be the rate of loss of PE, not so? Because the PE is being converted, right? If it's the rate of loss of PE, it will be this entire number, not this 0.10, it's the total energy. Or it could be the rate of gain You all understand what I'm saying? If you read the question carefully, this rate of energy conversion is not well qualified in the question. It could be the rate of conversion of P because the P is being converted. How much P is being converted? 77 by 10 by 500. This is the amount of P that is being converted to other forms of energy in 1 minute. So in one incarnation, it could be 77 by 10 by 500 over 60. And in the next one, it could mean, if you read it again, what is the average rate of energy conversion? The energy is being actually converted to kinetic energy. So it could be this number here, this entire number here divided by 60. So again, the question isn't clear. You might look at the mark scheme and they might give an indication, but the question for certain isn't clear as to what they're asking for. In any event, the rate of conversion of either potential energy or kinetic energy will be equal to the energy converted divided by the 60 seconds, the time taken, 60 seconds, okay? So either way it's going to be okay. At this point, is there any question you all have from these past papers that you found that you'd like me to do for you? I mean, time is really running out rapidly. An hour is almost up in that short time. Is there any question? Do you see any of these questions? All of these are questions on energy. All right. I want to look at this one here. This is one of the most difficult questions. Now, in fact, I'll talk you through it. This is June 1987. You don't have access to this question, so you can screenshot it and save this question, right? You all got it screenshotted? You took a screenshot? Yes. Celine, you took a screenshot?
Yeah.
Good. Let me just talk you through the question, right? We're looking at part C. In driving a rod 6 centimeters to the ground, a hammer with 4.8 joules of kinetic energy is brought to rest. The mass of the hammer is 2 kilograms and remains in contact with the rod throughout the blow. You know, like you've all seen somebody hammering a nail or something. It's a similar process. The hammer is being swung. The hammer has kinetic energy, and when the hammer hits the nail, that energy is being used to drive the nail into a piece of wood. So we all have a visual on this, yes? Now, the question is, calculate the resultant force which brings the hammer to rest. Just like the question we did today, I think we did a question in class, didn't we? Energy is equal to what? Force by what?
Distance in the direction of force.
Good. You understand that? So what has energy?
The hammer.
That's not what I just got a message here. A second. Huh? All right. Yeah, just reply to the question. So the hammer has this much kinetic energy. It's driving the rod 6 centimeters into the ground. So we have two parts of the equation here. We have the energy, which is 4.8. And we have the force, which we do not know what it is. That's what the first part of the question is asking. But we know that the distance is 6 centimeters. 6 centimeters in this equation must be represented as what?
Meters.
Right, so you have to go 0.06. You get so far? And from there, we can find what resultant force brings the hammer to rest. That is how we get it. Simple?
Yeah.
Next part is, what is the deceleration of the hammer? Well, deceleration is acceleration is equal to force over mass, not so.
Yeah.
And we just got the force. Anybody can tell us what's 4.8 divided by 0.06? 4.8 divided by 0.06.
18 newtons.
18.
It's a.
Mass, which is 2 kilograms. So we get that the acceleration is 20 meters per second squared. We good?
Yes, sir.
We got that's a deceleration, a negative acceleration. And the last part, what is the velocity of the hammer when it strikes the rod? Well, they gave us the energy, which is equal to 4.8 joule, right? 4.8 joule is equal to half mv squared, right?
Yes, sir.
Multiplied by m, which is 2, multiplied by v squared. So therefore, it's pretty straightforward to be able to solve that question and get what the velocity of the hammer is when it strikes the rod, right? It's a simple looking question when I solve it, but a lot of students, when they look at this question, they don't know how to proceed. But in the context of today, having done this equation, that energy is equal to force by displacement in the direction of the force, it brings it up. If you also asked for 1996, paper 3, goes back to 1996. Paper 3, this question is popular. Wow, those landed also hard. Is this question? Somebody couldn't get real loud there. Sophia can't hear. We're going to talk this question. This will be the last question. All right. I was just trying to mute people who turn in pages. So I can't hear most of you. You'll respond via the text, the chat, right? Respond via the chat. Now, this question is one of the more interesting questions. A wind power generator is an example of utilization of renewable energy source. Large blades are turned by the wind, and the rotation of the blades used to run the electric generator. The average speed of the wind is 10 meters per second, and the circular area swept up by the blade is 1,300 meters squared. Consider a cylinder of air passing over this area in 1 second. So this is the wind. The wind is moving at 10 meters per second, right? The area of the wind that is actually going to pass through and exert a force on the blade, that area is 1,300 meters squared. Now, the amount of air that is going to hit the generator or the blades will be 10 meter long. Now, this is something I need you to follow. Do you understand why it must be 10 meter long? Because all of the air that is here, that is, let's say the air at 5 meters away, in 1 second will more than pass the blade. The furthest molecule that will actually reach the blade, since it's moving at 10 meters per second, the furthest molecule from the blade that will actually pass the blade during that 1 second would be the molecule that is exactly 10 meters away. So all of these molecules in that 1 second would pass and exert a force on the blade. I'm seeing Sophia responding, and Sophia says she understands it. Everybody understand why all of these molecules of this cylinder would pass through the blade in that 1 second? Everything in the chat. Oh, voice.
Yeah.
Yeah? So what that means, sorry, so they said calculate the volume of air passing each second. So we have to find this, the volume in this piece, the cylinder. The volume of a cylinder is the cross-sectional area multiplied by the height, and that will be 13,000 meter cubed. So the volume is equal to 13,000 meter cubed. No problem there. That's the first part for 3 marks. Calculate the volume of air passing in each second. What is the mass of the air? Well, we know that the mass is equal to, mass of anything is equal to volume multiplied by
density.
right? And to key us in, they gave us the density of air as 1.3. So the mass of the air would be 13,000 multiplied by 1.3. So far, that would be the mass of air. That will be in fact in kilograms. No problems there, right? What is the mass of air? Calculate the kinetic energy of the air passing the blades. Now, once we found the mass, they already gave us the speed of the air, not so. If they gave us the speed and we now know the mass, we can work out the kinetic energy. KE is equal to a half m, which we just got, m by v squared. Right? K is equal to half m v squared. So that's, again, not a problem. The efficiency of the generator is 15%. Again, what does this mean? Efficiency is useful energy over energy supplied. All right? Calculate the power input, the power output of the generator. Efficiency is equal to useful energy divided by energy supplied. All of that is multiplied by 100 to express it as a percentage. So that's what efficiency is. Now, they've given us that the efficiency is 15%. So they've also given us what is kinetic energy. That kinetic energy is the energy supplied. The kinetic energy, this kinetic energy here, a half mv squared, that is, we know that. That is in fact the energy supplied. And of course, we're not going to make a mistake. I wasn't planning on making a mistake, but the 100 is still there. The reason why I'm using the 100 is you could have brought the 100 across, you know what I mean, and make it 0.15 as what they're suggesting. See, all right? So we really have to solve this equation for the useful energy. We will have a number for this from here. We have the mass, we have the velocity. So this is a number that we can generate. And the only unknown in the equation is the useful energy. So the useful energy after all of that would be equal to 0.15 multiplied by the kinetic energy. Yeah? You good? And you cross multiply and all that, right? So that's the question they're asking us. The question for the calculate the power output. That's the power output, the useful energy. Describe what happens if 85% of the energy which is not converted to electrical energy. What happens to that? I want you to specifically in the chat box type what you think happens to this 85%. Type what you think happens to that 85%. Don't rush to type all at once. only a very small part of it is converted to heat via friction. In fact, most of that 85%, is converted, is retained as kinetic energy in the moving air. And that's the best answer to the question. All right, when the air hits the blade, does the air stop and pile up on the blade? When this air hits the blade, does the air stop and pile up on the blade? What does the air do? The air continues.
Oh.
So, if you've ever put a fan, have you ever put a fan where the breeze is blowing? The fan is off, unplugged, right? The fan is unplugged, and you put the fan where the wind is blowing, and you see the blade start to spin. You ever seen that? Never seen that. The air that hits the blade still has kinetic energy. So they give some to the blade, but most of that kinetic energy is taken by the air, and the air continues to move in this direction. Clear? So most of the 85% that is not converted to electrical energy is in fact retained as kinetic energy of the air as it continues to go past the blade. A very small portion is converted to heat energy, but most of the 85% is kinetic energy of the air that continues to move past the blade. All right? So that is the best answer for that question, because we know the air doesn't pile up. The air doesn't just hit the blade and go here or go there. It actually hits the blade, pushes the blade, and continues flowing because it only loses some of its energy. All right, so we well past. I was planning to do just an hour of review with you all.
Sir.
I'm trying to really. Yeah, go ahead.
Huda asked why the 15 was not 15 over 100. Why was it not over 100?
That's right, but it is, isn't it? 15%, right? 15% is this divided by that multiplied by 100. When you transpose the equation, the 100 comes in the denominator and makes it 0.15. So exactly what she was saying here.
Okay, thanks, sir.
It's just that I was writing the equation the way the equation was presented, 15. So I didn't bring I was planning on putting it there, but that's the same thing, right?
Okay.
We good?
Yeah.
All right. So, Sophia, not following, do we consider molecules that do not hit the blade as the wind is moving at the speed of this? Yes, some of the molecules will not hit the blade because at any instant there'll be molecules slipping past it, here. All right. And that's part of what I'm seeing. That is, a lot of that 85% is kinetic energy of the molecules that continue to move, because there's only a part of the blade interrupting the airflow. This space here, and this space here, and this space here, at any instant molecules are passing through there. Only the molecules that hit these blades will give any of the kinetic energy. So the answer I said was, what happens to the 85%? Most of the 85% of the energy is kinetic energy of the air as it continues to move. All right? I hope that answers the question. All right, so I hope you all were able to follow the session. I hope it wasn't too fast for you. I hope there's some learning going on. I am available most of this evening into the night to answer your questions. So if there's any questions you meet that you have trouble with, feel free to email me, all right? And I can send answers to you as quickly as I get them, as quickly as I can write up any solutions, right? So good luck in the test tomorrow. I haven't really set the test, so I don't know what I'm going to put in. I'm hoping that I put one of these questions so you will feel happy with yourselves. I intend to bring a couple multiple choice questions as well. You're hearing that, right?
Yeah.
Yes.
Sorry? Hello?
Yes, sir, multiple choice.
Yeah, I can bring a few multiple choice questions, maybe 5. I'm thinking at least 5 multiple choice questions.
Okay, sir.
So I suggest you also look at some of the multiple choice questions in Dropbox. It will definitely be CSEC questions. I'll probably pull about 5 of them. Each of the multiple choice questions will worth about 2 marks. So that'll be 10 marks right there with the multiple choice, and whatever long questions I give you, it might be another 20 or so marks, at least. I haven't, as I said, set the testers yet. I'll do that in a little while. But I'm standing by for any questions you may have to be able to write up solutions and send it back to you as promptly as I can. So have a good night. Good luck in the test tomorrow, and I hope something that we do tonight comes tomorrow. I will try my best to bring something from what we did this evening. All right?
Okay. Thank you.
Thank you.
Bye.
Good night.
Good
Good
night.
night.
Good night.
Bye.
Good night.
Oh, you could type it.